Hello, this time we're going to look at light-emitting diodes. You may remember this simulation. It's a PN junction, which at equilibrium looks like this. But if I now put a voltage across this junction, causing an additional electric field to happen so that these electrons here can start moving, I can get to this situation here, where the electrons can come in all the way to the junction, drop down into the valence layer and head off. And to do that, I've now got electrons coming in here at the level of the conduction band, and electrons leaving on the p side at the level of the valence band. So I've had to put a voltage across my diode to do this equal to the difference between the conduction band and the valence band in electron volts. And if I do that, current is flowing happily, electrons are coming along and dropping down into the valence band of the p-type material. Now that's electrons losing energy, dropping into a lower energy state. Energy is conserved, so that energy has to go somewhere. And in many cases, that energy is released in terms of a photon of light. And if you design your diode so that that photon of light can leave the diode package, you end up with a very efficient light source. You can calculate the frequency of the light that is emitted by using the relationship between frequency and energy. The energy of a photon is the Planck constant times the frequency of the light. And the frequency of the light is the speed of light divided by the wavelength of the light. Now, the energy that is released is the energy difference between an electron at the bottom of the conduction band and the top of the valence band. And that has to be equal to the voltage that you've put across the diode in order to get the current to flow in the first place, or an appreciable amount of current anyway. So the amount of energy that an electron can use to produce a photon in a light-emitting diode is given by the charge on an electron, E, times the voltage that's across the light-emitting diode in order to get the current to flow and the device to light up. I've called it V gap in this case. It's equal to the difference in energy across the band gap in electron volts. That's equal to the Planck constant times the speed of light divided by the wavelength, which gives us, with a bit of algebra, the wavelength is equal to the Planck constant times the speed of light divided by the energy of an electron. And putting in the values for that, we end up with the wavelength in nanometers is equal to 1240 divided by the energy of the drop in electron volts, which is approximately equal to the voltage that you have to put across an LED to get it to light up. So I could just write this as 1240 divided by V, or VD, where that's the voltage across the diode. Well, red light has a wavelength of about 700 nanometers. So that implies that the voltage that you have to put across a red LED is approximately 1240 divided by 700, or about 1.78 volts. Notice that that is a lot more than the typical 600 millivolts that we assume is across a silicon PN junction in most circumstances. You can't make LEDs out of silicon. The band gap is too small. You need to make them out of other semiconductor materials which have a larger band gap. And the higher the frequency of the light that you want, the larger that band gap has got to be. Blue LEDs, which typically shine at about 480 nanometers or so, require a voltage across them of about 2.5 volts or so in order to light up. It's an important point to be aware of if you're trying to drive blue LEDs in particular from the output of a digital logic gate, which may only output about 3.3 volts as its maximum voltage. I should point out that these values are very approximate, and it's always a good idea to look at the datasheet of the LED. I have made quite a few approximations and assumptions in the models. I just wanted to give you some idea of the rough values that are required for the voltage drop across LEDs. Other than that, light-emitting diodes behave pretty much like any other diode as well. You can approximate their behaviour using the Shockley equation, and they pass current happily in one direction, but not the other. Next time, just a few words about reverse bias diodes, and why you might want to take a diode, which is not a Zener diode, and put it in a circuit such that it has a reverse bias across it.